Now that we know what the sine and the cosine function are, the next thing we need to talk about is how to graph these functions. So if I wanted to graph f of x equals sine x, okay, this function, the sine function, well, it's important to understand what the domain and the range for this function are. We've already talked about this, that the domain and the range for these functions, sine and cosine, well, the domain is negative infinity to positive infinity. That's for both functions. And the range is negative 1 to 1. And the idea is, if I'm looking at this particular function, I'm plugging an angle in there. So that's where my angle's going, theta. We could call it x, we could call it theta, it doesn't really matter. But I'm going to plug my angle in there, and I can plug any angle into this function. I'll always get a y coordinate out of it. The answers I get out of this function, which is the range, will always be y coordinates between negative 1 and 1. Now, graphically, that has some consequence in that the domain are all the x values. If this is the x-axis and this is the y-axis, the domain is the values along the x-axis, and the range are the values along the y-axis. So when it comes to the y-axis, my y-axis values will always be between negative 1 and 1, but my x values can range from negative infinity, that's an infinity, all the way up to positive infinity. So my graph's going to go as far as possible left and right, but vertically it's going to be stuck between negative 1 and 1. Okay? Alright, so let's erase this. And let me show you what the graph of sine looks like. So the graph of the sine function looks like this. And it just essentially has this wave pattern over and over and over again, infinitely in either direction. This wave pattern is what we call the sine wave, or a sinusoidal wave, or simply just a sinusoid. The y value where this thing maxes out, sort of the top of the wave, if you sort of follow this all the way across, the top of the wave will be at 1, the bottom of the wave should be at the same point the whole time, and my graph doesn't look that great, but the bottom of the wave all the way across should be the same. That would be at negative 1. Okay. And what happens is, this pattern is a repetitive pattern. And whenever your graph has this repetitive pattern to it, we say that the function itself is a periodic function. And the distance it takes for the graph to repeat itself is the period of the function. So I'm going to look at a couple of key points. Here, this point, my x value is 0. Here, this point, that's the maximum it reaches. My x value is pi halves. Here, pi. Here, 3 pi halves, and that's where its minimum is. And then here again, 2 pi. And what happens is, after that point, this pattern that I have from here to here will repeat itself again, and I'm going to get another loop, and then another loop, and another loop, and it's just going to do this again, and then this again, and then this again, and so on. Now, why do I get these points? Well, if I plug pi halves into the sine function, if I took the sine of pi halves, I would get 1. So I have this point here of pi halves, comma 1. And so on for all these. If I plug pi into the function, if I took sine of pi, I would get 0, which is the same thing as the sine of 0, which is the same thing as the sine of 2 pi. That's why the y value here, here, and here are all 0. And then 3 pi halves, I'll get a value of negative 1. These 5 points, this point, this point, this point here, this one here, and this one here, are the key points to drawing the graph of a sine function. And this, what you're looking at, is one period. The period will start here and end here, because then after I get to that point, my graph will start over again. So the period for this function is 2 pi. It's this distance. The total distance from one value to the other value where the graph repeats itself is the period of this function. Alright, so let me clean some of this up. Get rid of some of these things here. Alright. And we call these 5 points the key points because if I know where these 5 points are located, I can draw this graph because I know that I have my x-intercepts, I have my maximums, my minimums. You know, if I picked other 5 random points, like if I said this point, this point, this point, this point, this point, there's 5 points. But I want to consider those key points because if I have those 5 points, I can't draw the entire period of the sine graph. However, if I know, you know, this point here, this point here, this point, this one, and this one, if I know where these 5 key points are based off of these x values, in this case, this x value, and this x value are x-intercepts, this one's a max, and this one's a min. I can connect those dots, and I could fairly accurately draw one period of the sine function. So what you need to become accustomed with is knowing what the graph of a sine function looks like, and where the 5 key points are located and what they represent. The ends of the period are x-intercepts. Directly in the middle of that period is another x-intercept. Between these two x-intercepts, I have a maximum, and between these two x-intercepts, I have a minimum. And just like we graphed other things, if you know what the graph looks like before you start, then all we have to do is alter that graph. If we're going to move it to a different location, we're going to stretch it out, we're going to flip it over, we're going to do any transformation. If we know what the graph looks like to start, we know how it's transformed, then we can re-represent the graph in a different location. Now we need to look at the cosine function. So if I wanted to graph the function f of x equals cosine x. Okay. So this is the cosine function I want to graph. Well, for the same reason, this graph is going to have this wave pattern. It's going to have, and we still call the graph of this thing a sine wave, even though it's the graph of the cosine function, because generally it looks fairly similar to the sine function's graph, but the graph is a little different. So let me just graph it, and then I'll explain kind of where the points come from. So just like the sine, it's going to max out at 1, and it's going to have a min at negative 1, because the range for cosine is the same as the range for sine. But what happens is it looks a little different in that it's going to look like this. Now, if you look from afar, it looks the same. If I just back this up a slide, you see the sine function, you see the cosine function. They look fairly similar, but there is a slight difference in that if I look at when x equals 0, for the sine function, if I draw the sine function in yellow, the sine function looked, if I can do this accurately, let's see, not the greatest picture, but for the sine function it looked like that yellow picture in that, you know, at 0 the sine had an x-intercept, but at 0 the cosine function has this point here, 0, 1. And that's because if I find f of 0, basically take the cosine of 0, I would get 1. You get different values when you take the cosine of a certain angle or certain value than you do with the sine function. Alright, so let me erase this yellow picture and let's go back. Alright, so then there's key points to this graph. The key points are located here. Okay? And if I can find where these locations are, then I can draw a period of the cosine graph. And that would be one period of the graph, because if once I get to here, my graph will repeat itself. So one period of the cosine looks like that. Okay? As opposed to one period of the sine looks like that. But as a whole, when you step back, they both kind of look like the same graph. Alright, so where are these located? Well, located basically in the same locations. This is going to be pi halves. This one right here is going to be pi. This one here is 3 pi halves. And this one here is 2 pi. We use the same key points, but the key points relate to different things. For the sine function, 0 was an x-intercept, but now 0 is going to be a max. For the sine function, pi halves was a maximum. Now for the cosine, it's going to be an x-intercept. Pi was an x-intercept for the sine, and now it's going to be a minimum. 3 pi halves was a minimum for the sine function, and now it's going to be an x-intercept. And 2 pi was an x-intercept for the sine function, and now it's going to be a maximum. Okay. So the key points as far as the x values go are the same, but for what they represent, it's different. So this is what the cosine function will look like, and you just get it by taking different values and plugging them into the cosine. Now, one thing I just want to explain real fast is if you look the way I'm incrementing the x-axis, okay? Essentially what's happening here is I'm incrementing the x-axis based off of pi halves, pi, 3 pi halves, 2 pi. Right? These are the values I'm using on the x-axis. Typically when you make an xy chart, you would label your x-axis 1, 2, 3, 4. But that actually is not convenient for us, because I have to take these x values and plug them into the function. Well, if I have to plug 1 into the function, I have to find cosine of 1. If I have to plug 2 into the function, I have to find cosine of 2, and cosine of 3, and so on. Well, these are not easy things to do. But what is easy for us to do? Find the cosine of pi halves, find the cosine of pi, 3 pi halves, 2 pi. And these are just numbers. Pi halves is roughly 3.14 divided by 2. If you want to estimate it even more, it's 3 over 2, or 1/2, or 1.5. Okay? So technically this is a number on a number line just like any other number, but I'm using these particular values, pi halves, pi, 3 pi halves, because they're easier to work with this function as opposed to 1, 2, 3, 4. But 1, 2, 3, 4 are in there as well. I'm just not writing them down. Let me erase some of this. Erase some of this. Okay. The idea is, okay, so pi halves is like 1.5, right? So that tells me that 1 is probably right around there. 2 is probably right around there. 3 is right around there because pi is 3.14, right? And I could increment my x-axis 1, 2, 3, 4, 5, but it just isn't convenient for this particular function. So we use the values that are most convenient for a particular function. For trig, it's these things that relate to angles: pi halves, pi, 3 pi halves, 2 pi, etc. So what you need to do is you need to make yourself familiar with the cosine function and what one period of the cosine function looks like, and also the sine function and what one period of the sine function looks like, and where these key points line up. Because if you know that, then the next thing is, okay, now we're going to start altering these graphs. If we start altering these graphs, how are we altering them? Well, we're doing transformations. We're going to shift them to the left, shift them to the right, up, down, all those things that you've talked about previously. Alright, so now we need to start altering our graph. So the first thing we're going to do is we're going to look at, what if we multiplied our function by some constant? A is going to be just some number, okay, a constant. And if I multiply my function by a constant, how does that affect the graph? Well, we've done that before. We've talked about if I look at the function, say f of x equals x squared, as opposed to, say, g of x equals 2x squared, or h of x equals 1/2 x squared. How did that affect the function? Well, what it did is it stretched it out or shrunk it down vertically. So this number right here, being bigger than 1 or less than 1, would stretch it out or shrink it. Well, it's the same thing it's going to do with these functions, right? If this value a is greater than 1, it's going to stretch it vertically. If a is less than 1, then we shrink it. Now we're looking at the absolute value of a, because if a is negative, we've also talked about what that does. That would flip the graph over the x-axis. So we don't want to talk about flipping it. We only want to purely talk about how this number would affect the vertical height, so stretching or shrinking. And so if my regular graph is normally between -1 and 1, or sorry, +1 and -1, okay, if that's normally where my graph would be, either sine or cosine, right? So it would look like this, stuck between these two values. If I'm going to change this vertically, say by stretching it out or shrinking it down, then that's going to change what these values are between. And essentially the values I'm going to be between are going to be between negative a and positive a instead of negative 1 and positive 1. So that's how we can start to alter the graph, stretching it or shrinking it vertically, and we do that by a multiplier in front of our function. We still have to know what the function looks like originally, though, to be able to then adjust that. Okay, now this value out in front relates to something called the amplitude. The amplitude is essentially the distance from the center of the graph to the outer edge of the figure. So this distance right here would be considered my amplitude. Okay? Or essentially you could say it's half of this total distance from top to bottom. Either way you look at it, it's a distance, and the distance has to be positive. So what we do is to find the amplitude, we look at the absolute value of a, because we don't want to look at the fact that if a is negative, that might flip the graph over, which we'll talk about in a second. So if you want to find the amplitude should always be the absolute value of a, because if my graph is between positive a and negative a, then half of this distance, which is 2a, would just be a itself. Right, that would be this distance here, would be a, and this distance here would be a. What I see students make a lot of mistakes on is that they don't do the absolute value of a when they find the amplitude, they do just a itself. Amplitude should always be positive. You can never have a negative value for your amplitude. Okay, so let's do an example. So I want to graph y equals 2 sine x. Well, in this case right here, a is 2. So my amplitude is 2. Now how does that affect my graph? Well, vertically, instead of being between negative 1 and 1, my graph is going to be between negative 2 and 2. Other than that, everything's going to stay the same. A period for my sine function should still look like this. So if I'm going to use one full period to graph the sine function, my one period would have this shape to it. Just my y values are going to be between negative 2 and positive 2. This value would still be 0, this would still be pi halves, this one would still be pi, this one 3 pi halves, and this one right here would be 2 pi. Okay? And knowing where these values are is important. So the maximum, the minimum, they're located at pi halves and 3 pi halves. Your x-intercepts are at those other three locations. If I look at this comparative to what the sine looked like originally, well, here would be 1, here would be negative 1, and my original sine graph would look something like that for one period. But I stretched it out vertically in either direction, so this stretched up and this one stretched down, and now I'm between negative 2 and 2. So changing your graph via the amplitude is actually really easy to do if you know what the graph looked like originally. Alright, how about these two? I want to sketch these two graphs on the same plane so you can see the relationship between them. But if you look at it, this one has a 1/2 in front, this one has a 3. So the amplitude for the first one is going to be 1/2, and the amplitude for the second one is going to be 3. So let's draw the first one. So here would be, say, positive 1/2, here would be negative 1/2. Okay? So I'm going to draw one period for the cosine function. And when you're drawing these, you really should draw the whole graph. But most of the time, all we're really concerned with is what does one period look like. Because then all you have to do is replicate that. So if I drew one period for the cosine graph, it should look like this. Okay. Now it's going to continue on over and over and over again in all directions. Okay. But that's what one period would look like. My x values are 0, pi halves, pi, 3 pi halves, and 2 pi. Okay, that's where we get the maximum, x-intercept, minimum, x-intercept, maximum again. Right. Now if I wanted to draw the cosine in the same plane, let me choose a different color. Okay. That one has an amplitude of 3, so I mean this is going to be totally accurate, but let's say 3 is up here and negative 3 is down here. My graph is stretched, so now it starts here. Now the x-intercept is still going to be exactly the same spot, because what happens is I'm going to stretch the graph equally in both directions. So if I'm going to stretch it equally this way and this way, anything that's in the center, which is the x-axis, is going to stay exactly where it is. And then my graph is going to continue on and on and on. This isn't 100% accurate, but that's pretty close. So that's the difference between the two, the blue being the 3 cosine, the red being the 1/2 cosine. Okay. There's one other thing that can happen here, and that's with the reflection. Now if I look at this problem right here, okay, the amplitude for this function is positive 3. Because in order to find the amplitude, we look at this number out in front and we take the absolute value of it. That number out in front does two things. It stretches it vertically, but then the sign of that number could flip the graph over. Remember, if we multiply our function by negative, it's a reflection. We talked about this when we did transformations. So that number does two things. The stretching part is the amplitude part. The flipping over is a reflection, completely different. So if I'm going to go graph this function, I'm going to be between positive 3 and negative 3. Now it's a sine function. Okay? Normally a sine function would look like this for one period. 0, here's pi halves, here's pi, here's 3 pi halves, here's 2 pi. And it's going to continue on and on over and over and over again. So I'm just going to do that. But let me change my color again. I have to flip this graph over, right? I'm stretching it out, having an amplitude of 3, but I also have to flip this graph over the x-axis. When you have a negative in front, you flip over the x-axis. So what's going to happen is this graph's going to actually end up looking like that, because I'm flipping the whole thing over the x-axis. So we'll just continue this on. And that red graph is actually the graph of this function. Alright, so you now know how to change the amplitude of your function and how to flip the graph over the x-axis. So we've talked about how we can stretch our graph vertically. The next thing we have to do is talk about how we're going to stretch our graph horizontally, which is a fairly new concept. Previous functions we've talked about stretching our graphs out. We've only done vertical stretches, but since these are really like horizontal functions, they move horizontally, we need to also talk about how stretching it horizontally would work. Now typically with anything you do to change your function, it's all determined basically by what you're doing either outside the function or inside the function. Are we adding outside or are we adding inside? Subtracting outside, subtracting inside. Are we multiplying outside or inside? And if you do anything outside the function, it usually affects the graph vertically. If you do anything inside the function, it affects the graph horizontally. And that's what we're going to do here. What's going to happen is we're going to multiply the inside of the function by some constant. And that's what this b is representative of. The a, which is multiplied outside the function, affects the graph vertically. But this b, which is multiplied inside the function, affects the graph horizontally. Now what's going to happen is it's also going to do the opposite of what you think is going to happen, because that's kind of the way the inside works. I mean, think about it. When we looked at this, I say, okay, here's a function, y equals x plus 2 squared versus y equals x squared plus 2. I'm adding 2 to the function in each case, but here I'm adding 2 inside the function, and this one I'm adding 2 outside the function. Well, what's that? This would change the graph horizontally, this would change the graph vertically, in that here I'm going to shift my graph to the left. Here I'm going to go up. And when I do it inside, okay, it kind of goes the opposite of what common sense would tell you, because I'm adding 2. You would think if I'm going to go left or right, I should go right, but it kind of does the opposite. Well, same thing goes here. So if I get rid of some of this, normally when we multiply by a value bigger than 1, it stretches it. When we multiply by a value smaller than 1, it shrinks it. That's vertically, and that's true, but horizontally, it's the opposite. If my value b is less than 1, then my period will be bigger, which means it's going to stretch it horizontally. Okay? And if my b is bigger than 1, my period is going to get smaller, which means it's going to shrink horizontally. Well, if I'm stretching and shrinking it horizontally, if my graph looks like this, and I'm going to stretch it or shrink it horizontally, well, it might start to look like this instead. That would shrink it down. Think of it like an accordion going in or going out. And if I'm doing that, I'm affecting my period. So how is the period going to change? Well, b is going to affect the period. And the way we can calculate what the new period is going to be is to use this little formula. I'm going to take 2 pi and divide it by b. And this will tell me what my new period is going to be. And that period is the distance from one end to the other end. This distance here. That would be my new period. And what we're really doing is essentially, if you look at this 2 pi over b, we're taking the old period and dividing that by b. Because the old period for sine and cosine were both 2 pi. That's going to be important, especially when we talk about other trigonometric functions. Alright, so I want to draw the graph of y equals x, or y equals sine of x over 2. So if I'm going to draw this graph, in this case I can write this as y equals sine of 1/2 x. It's the same thing. Now, what this is looking like is y equals sine of bx, b being 1/2. So my new period is going to be 2 pi divided by 1/2, or 4 pi. Now if my period is going to be 4 pi, that means the distance from one end to the other end has to be 4 pi. So if this is what my sine looks like for one period, I'm going to start at 0 and I'm going to end at 4 pi. So that the total distance is 4 pi. Well, if that's the case, this x-intercept is directly in between these two. Well, if it's halfway between, that means this is 2 pi. And I can always figure that out if these numbers aren't very easy to work with, which right now they are. But if I have to figure that out, if I have two numbers on a number line, let's say, I don't know, 5 and 9, and I find out which one's in between them, 7 obviously, I can get that number by taking these two, adding them together, and then dividing by 2, essentially finding an average. So I get 14 over 2, which gives me 7. So anytime you want to find some number in between two more numbers, that's how you do it. So if I take 0 and 4 pi, I add them together, divide by 2, I get 2 pi. That's in the middle. Alright. So then I want to find what this point is. Well, this point's going to be pi, because that's directly in between these two. And this one's going to be 3 pi, because that's directly in between these two. It still maxes out at 1. It still mins out at -1. This is what my graph will look like. Comparative to what the original sine looks like, you know, for just y equals sine x, where I don't change the period, it's going to look like this. Yeah. Okay? Which means the original sine would have 2 full rotations in the time that it takes this one to do 1 rotation. Now remember that this graph really just continues on infinitely in all directions, okay? But this would be 1 period now of this new one, so this period has now changed. Alright, what if I gave you a question that said, find the period of, say, y equals 3 cosine 5x. Okay, well, this is a cosine bx, b being 5. So the new period is the old period, which is 2 pi, divided by b, which is 5. So that's my answer. 2 pi fits. That's the period of this function. If I said, what's the amplitude? The amplitude would be a, or in this case, absolute value of a, but it's the same thing as a, and I get 3. Alright, how about another one? Period and amplitude of y equals negative 1/2 cosine of x over 4. In this case, a is negative 1/2, b is 1/4. So my period is 2 pi divided by b. So in this case, 2 pi divided by 1/4. Flip and multiply, you get 8 pi. My amplitude is the absolute value of a. Absolute value of negative 1/2 is 1/2. So period of 8 pi, amplitude of 1/2. Okay? Now we want to start getting into translations, horizontal shifts, left, right, up, and down. So let's do the horizontal ones first. So we're going to do these horizontal shifts. Amplitude is not really affected by this, but period is, in that period is a horizontal stretch, and then we're also going to do a horizontal shift. We could do each one separately, but actually what's going to happen is we're going to do them at the same time, because it's just easier to do the computation all at once than in 2 separate steps. Alright, so if we look at our function, we know a affects the amplitude, b affects the period, and now this new value, c, is going to affect the horizontal translation. And what we're doing is we're subtracting or adding, because this could be a plus in here, we're subtracting or adding inside the function. And another key to this is that b is factored out. This b value being factored out is going to be pretty important, because the way you look at this can change what you think of as c. So it's got to be in this form where it's b times x minus c. Okay? And same thing goes for cosine. And that c value is going to affect the horizontal shift. Now, what I could do is I could say, alright, well, here's a function. Y equals sine of 3 times x minus 2. And what I could do is say, okay, well, I'm going to change the period using this number, and then I'm going to shift it using this number. And I could do those two things separately. But changing the period is going to change it horizontally, in that it's either going to stretch it or shrink it. In this case, since b is bigger than 1, it's actually going to shrink it down horizontally. And then what I'm going to do is this one, since I'm subtracting 2, that should move it to the right 2 units. And I can do those two things separately. But then I have to draw 2 graphs, one where I change the period, then after I change the period, then affect the shift. What we're going to do actually is look at them at the same time. The way you do that is you say, okay, this bx minus c thing is going to do both change the period and do the horizontal translation. So what I'm going to do is I'm going to say, alright, well, if I know where the ends of my graph are located, so here's a sine. The ends of my graph are located here and here. If I'm going to change the period, these endpoints are going to change either in or out, okay? And then if I'm also going to shift it, those endpoints are also going to change. Either everything's moving to the right or everything's moving to the left. So if I can figure out where these endpoints move to, then everything inside the graph should move in the same way. So if this bx minus c is going to do all this movement, what I'm going to do is I'm going to take this bx minus c, I'm going to set it equal to the original endpoints of the graph. Well, this endpoint here was at 0, this endpoint was at 2 pi. For cosine, it's the same thing. Now the endpoints happen to be different types of points, but still this end was at 0, right? And this end was at 2 pi. So if this bx minus c is going to affect horizontally what's happening to the graph, it's going to change those endpoints. I'm going to set that bx minus c equal to the old endpoints, 0 and 2 pi. And if I solve these two equations, that's going to tell me where my new endpoints are, and then all the key points inside the graph are going to move with it, and then I can redraw my graph. So, if I give you an example, alright, say y equals sine of 4x minus pi. I'll put parentheses because that's going to be important. I'll talk about that in a second. And I said find the end points of one period. So I'm going to take this 4 times x minus pi, set it equal to 0, 4 times x minus pi, set it equal to 2 pi, and solve these two equations. That's where my new endpoints are going to be for one period. So what I'm going to do is divide by 4. I get pi minus x equals 0. Add pi, x equals pi. So that's one endpoint. The other endpoint, divide by 4. X minus pi equals pi halves, because 2 over 4 is a half. And then add pi. Pi halves plus pi is 3 pi halves, and this is my other endpoint. So these are now my new endpoints for my function. Now let's take a second to check that. This value right here will affect the period. This will be the horizontal shift. My new period should be 2 pi divided by b, in this case 4, so pi over 2. Okay? That should be the period. Well, if these two values here are the endpoints of one period, the distance between them should be the period. Well, you find the distance between any two numbers on a number line by subtracting them. So if I want to check to see if these numbers are right, if I know what the period's supposed to be, then I can check to see if those numbers are right by subtracting them and getting that period. So if I do 3 pi over 2 minus pi, I should get pi halves. This endpoint minus this endpoint should give me the period. And it does. Okay, 3 pi halves minus pi does give you pi halves. So this is what I'm talking about. Now, if I just talk about the parentheses for 1 second. Let me erase some of this. So if I give you something like this, y equals sine of 5x minus pi, and I write it like this, well, this is not going to tell me what the period is, or what the phase shift is, which is another name, just so I clear this up. The horizontal translation, another name for the horizontal translation, is the phase shift. So this is not going to tell me accurately what the phase shift is, because I don't have it in the form I want. The form I want is b times x minus c, and this isn't there. What I have to do is factor b out, essentially. B being this coefficient in front of the x. So if I want to write it this way, what I really should do is write this as sine of 5 times x minus pi over 5. Now what that is if I multiply the 5 back in, I would get 5x, and if I multiply 5 times this, 5 and the 5 will cancel, I'll just get with a pi. So these are the same, but looking at it like this, it's in the form that I want, and I see, okay, this number is going to affect my period. Now remember, this number is not the period, but this number helps you get the period. This number right here, however, is the phase shift. C is the phase shift. Pi is not. Pi fifths is. So if I'm looking at it this way, I'm not going to see the phase shift properly. I always have to factor the 5 out so that I can then see that phase shift more accurately. And this is where this comes in. Okay? So let's do an example. So sketch the graph of y equals 1/2 sine x minus pi thirds. Alright, so there's two things here that's happening. This number, oh, wrong thing. this number right here and this right here. This one right here is going to affect the amplitude, and this one's going to be the phase shift. Now, the amplitude's going to be 1/2 because it's positive already, and my phase shift is going to be pi thirds. Now it's going to be pi thirds, and since I'm subtracting pi thirds, I'm going to be to the right. Okay. Now, the best thing to do when you're trying to do this, if you're going to redraw the graph, is to say, okay, I'm going to move the graph pi thirds to the right. Now I don't want to sit there and have to move every single point pi thirds to the right. So what I'm going to do is I'm going to take this x minus pi thirds, I'm going to set it equal to 0, and x minus pi thirds, set it equal to 2 pi, which is going to move these 2 points. In this case, I'm going to get x equals pi thirds, and x equals 2 pi plus pi thirds, which would give you 2 pi would be 6 pi 6 pi thirds plus pi thirds gives you 7 pi thirds. So now these are my endpoints, and then from there I want to start to put my graph together. So I go, alright, well, here's pi thirds, here's 7 pi thirds. I'm just randomly putting them there on the x-axis. My amplitude was 1/2, right? So I'm going to start at 1/2 and go down to minus 1/2. One period of the sine should look like this. Okay. Maxing out at 1/2, minning down at minus 1/2, starting at pi thirds, down to 7 pi thirds. And then we're going to fill in the points inside. Well, this point right here is another point on my x-axis. Well, it should be directly between pi thirds and 7 pi thirds. How do we do that? We said already, if I want to find that point, I should do 7 pi thirds plus pi thirds divided by 2. Add together, divide by 2. 8 pi thirds over 2 is 8 pi sixths, which is the same thing as 4 pi thirds. So this would be 4 pi thirds. Alright, then I want to figure out where this point is. Well, this point right here would be located directly in between these 2 points. Well, if I add those together, I go pi thirds plus 4 pi thirds divided by 2. I would get 5 pi thirds divided by 2, which gives me 5 pi sixths. So this one would be 5 pi sixths. I do the same thing for this one. Add these two together, divide by 2. I'm going to get 11 pi sixths. Okay. So this would be the graph of that function. And this is really the detail that you need. You don't need more than this, but less than this really wouldn't be enough. What I have is my key points labeled. I have the x values labeled for them. I have the y values labeled. So I basically have all these points labeled, and I have one period drawn. Now remember, this period is going to keep going over and over and over again, but that's usually enough for what you need to do with this function. Alright, let's do one more of these. So here's another one. Y equals -3 cosine 2 pi x plus 4 pi. So I'm looking at this. Alright, this number here is going to affect the period. We're going to have an amplitude and a phase shift, but we're not looking at it correctly here. So what I'm going to do is I'm going to rewrite this. -3 cosine of 2 pi times x plus 2 pi. I'm factoring a 2 pi out of that inside. And now I see this. My amplitude is going to be the absolute value of -3, which is 3. My period is going to be 2 pi divided by 2 pi, because this is my b. That's going to give me 1. And this is going to be my phase shift. Alright, but now I got to draw this. Best thing to do is first find your endpoints. Okay. So I do that by taking this inside part, and it doesn't matter which way you look at it, whether you look at it this way or you look at it this way. Take the inside part, so 2 pi x plus 4 pi, set it equal to the old endpoints, 0, and 2 pi x plus 4 pi equals 2 pi, and then solve for x. So I subtract 4 pi, I get 2 pi x equals negative 4 pi. And then I'm going to say divide by 2 pi. I get x equals negative 2 pi. So that's one endpoint. Same thing, 2 pi x, subtract 4 pi, I'm going to get negative 2 pi. Divide by 2 pi. I'm going to get x equals, x equals negative 1. Sorry, this first one here, this shouldn't have a pi, right? Because these pi's are going to cancel. So I'm just going to get negative 2 and negative 1. Again, same thing, pi's cancel. Alright, so these are the endpoints of my graph. Well, remember, look at this. Period was 1, right? What's the distance between negative 2 and negative 1?
1. So if you see, they match up. And that's something you can always use to check to see if you're doing things right. Alright, so now we want to start putting this graph together. Alright, so if we go back, our amplitude was 3. So that means we're going to go from positive 3 to negative 3. Okay? And our period was 1. Our endpoints were negative 2 to negative 1. Okay? Now normally your cosine looks like this for one period. Okay? And then again it's going to continue on and on and on over and over again. Right? In either direction. But this would be one period. Now remember, if you go back to our original function, there's a negative there. Okay? So that negative is going to flip it over. So if I change my color a little bit, so you see the difference, my graph's going to look like this for one period. Okay? And it's just going to continue on and on and on, and so on. Okay? Now, we just got to label things a little bit better. So we have these points here on the ends, which normally are maximums, have flipped over now are minimums. Directly in the middle, which we could say negative 1.5 is a maximum. These two x-intercepts, we're going to label those as negative 1.25 and negative 1.75. And that would be, the blue graph will be the graph of this y equals negative 3 cosine of 2 pi x plus 4 pi. Okay? Alright, so we have one more thing we need to cover. Okay, so here we got the vertical translation, the last thing we need to cover. So we know what A does. If we look at this, we know what A does, we know what B is going to do, we know what C is going to do, and now we have this D value. If you look, the D is added to the entire function, which is a lot like if I said, you know, x squared plus 2, right? When we would add something to the entire function, it would move it up or down. In this case, adding up, subtracting would be down. Same thing's going to go here for these functions. Okay, so if we're going to add something to the function, this D value, if it's positive, is going to move it up. If it's negative, it's going to move it down. Right? And that goes for sine and cosine. So A has something to do with the amplitude, B, period, C, phase shift, D, vertical shift. Now, remember, A is not always the amplitude. The absolute value of A is the amplitude. B is not the period, but 2 pi divided by B is the period. C is the phase shift as long as you look at it in the right way and that B is factored out. So you look at it as B times the quantity x minus C. And D is outside the whole function. That would be our vertical shift. So let's say I wanted to graph this particular function right here. I could rewrite this function another way. I could write this as 3 cosine 2x plus 2. Now normally we don't write it that way because a lot of people might take this plus 2 and think that it's inside the function with this 2x. But it's not, because there's no parentheses. If it was inside the function, I would put parentheses like this. And that would say that it's inside the function, but it's not. So when I see a function like this, it's this plus 2 is outside the function. And to really make that clear, we just put that plus 2 in the front, and then you have no question as to whether or not that it's outside the function. So the function's multiplied by 3, that's my a. Inside the function's multiplied by 2, that's my b. And I'm adding 2 outside my function, that's my d. There is no phase shift here in this one. Alright, so I say my amplitude is going to be the absolute value of 3, so just 3. My period is going to be 2 pi divided by b, in this case 2 pi divided by 2, so that's pi. And I have a vertical shift 2 units up. Alright, now we want to still figure out where our endpoints to our graph are going to be, and you can still use the same method of, I'm going to take the thing inside the function, that's 2x, set it equal to 0, set it equal to 2 pi, solve those two equations. Here I'm going to get x equals 0, here I'm going to get x equals divided by 2 pi. These are my endpoints. The distance between these endpoints is the period, so that matches up. And again, you want that to match up. If it doesn't, you messed up somewhere. So now we want to start putting this graph together. So what did we say? We said the endpoints were going to be 0 and pi. Okay. The amplitude, if we go back, the amplitude was 3, and we had a vertical shift of 2. Now, here's the thing. Our amplitude's 3, so normally we would be between positive 3 and negative 3. But we shifted this up 2 units. So this whole amplitude goes up 2 units. So now, instead of between negative 3 and 3, I'm actually going to be between 5 and negative 1. Also, where the x-axis is moved up 2 units as well, so that's going to be at 2. So think about this like it's the center line of the graph. You know, that's where the x-axis was, and it moved up. The x-axis is kind of the center of your graph. My picture's not that accurate, but then this is going to be my minimum of my graph, and this is going to be my maximum of my graph. And this distance from here to here should be equal to this distance. In my picture it doesn't look that way, so let me correct that a little bit. Let's move this 5 down. So I'll put the 5, say like there. That looks a little bit better. So there's 5. That's the maximum of my graph. Alright, so we're talking about looking at a cosine function. Remember, it was y equals 2 plus 3 cosine 2x. So if we're looking at a cosine function, we start the cosine function up high, then that function should be ending high directly in the middle, should have its minimum point, and kind of in between those, which would be about there and there, should be our x-intercepts, and my graph should look like this. Okay. Now, I said these were x-intercepts. They're not on the x-axis. That's where the x-axis used to be. That's where they used to be x-intercepts, but I moved those x-intercepts up 2 units. So that's my graph for my vertical shift. And it's not that much more difficult to do. You're just taking your whole graph and moving it up or down and sort of re-represent where the x-axis moved to, where the top of the graph moved to, where the bottom of the graph moved to, and you can do this. And remember, this graph's just going to continue on over and over again.